Hello, everyone. I'm Junchao from Argonne. Introduce the integration of PETSc, Tau, and the Kokkos-Core and Kokkos-Kernels. So I will introduce how PETSc came to Kokkos, and then the integration of PETSc, Kokkos, and features we used, and the difficulties that concerns in deeper integration. So what's the PETSc Tau? PETSc stands for Portable Extensible Toolkit for Scientific Computation, and Tau for Toolkit for Advanced Optimization. Tau was a separate package before, but now PETSc and Tau, the two packages are combined. So PETSc stands for PETSc and Tau. PETSc was the first widely used distributed numerical library, and it provides a large suite of solvers, solvers, linear and nonlinear, and time-stable optimizers. And PETSc is the backbone of diverse scientific applications. This slide shows science domains using PETSc. You can see a lot. From this scientific impact index numbers, you can see PETSc's impact. We have tens of thousands of users, and mainly citations and external packages by Kokkos and Kokkos-Kernels are one of the external packages. Actually, with download trading loss, you can also use trading loss through PETSc. And we have many toolkits that use PETSc. By toolkits, I didn't mean a single application. Most of them are framework or toolkits that you can build a large number of applications. For example, the moves from Idaho National Lab for nuclear reactor simulation. And also, PETSc is a member of New Focus Foundation. I want to mention that because we joined the New Focus even before the debut of HPSF. I didn't know whether it's possible, it's moral or legal for us also to join HPSF. I didn't know that. So let me introduce PETSc's OO design. You know, PETSc is written in C, but we have object-oriented design, and we have classes and hierarchies. You see, these various vector class, for example, vec sequential, vec MPI. For CUDA, we have vec sequential CUDA, vec MPI CUDA, and for Kokkos, similarly for PETSc matrix, we have this class hierarchy. And in C, we do that through the Porter-to implementation. You may be already very familiar with this scheme. In the public header, we have define type to a porter, and then in the private implementation, we define the structure, and I want to point out, for example, in this structure, P-VEC, this private data structure, we have a very large function table, and we install function pointers in this table so that we can different subclasses. For example, for VEC sequential, by runtime selection, we can go through either sequential implementation or LPI implementation of the vector. So then how PETSc come to Kokkos? PETSc is portable, performance portable, but by performance portable, I mean PETSc can run various CPU architectures or GPU architecture now, and PETSc can run different OS, laptops, workstations, supercomputers, and different networks, and PETSc always work towards robust performance code on emerging hardware. but before GPUs, the portable in PETSc, the P really meant PETSc was for C and MPI. PETSc played important role in the birth MPI. In this diagram, we show PETSc developers and the PETSc and MPI releases. You can see Bill Group and Barry Smith, the original PETSc developer. They involved in MPI standardization and PETSc implementation. From this deep involvement, we have very successful MPI stand, and they use in PETSc. The C plus MPI approach hold even under the temptation of OpenMP. We tried to add OpenMP in PETSc, but later we go up. I just put the code from Barry Smith, the original author of PETSc, to show why we didn't choose OpenMP. But the C plus MPI approach failed with the development of CUDA. You may all know the reason, because C the MPI were designed way before GPUs. So with CUDA, we have to support the GPU. We come up with these three strategies. We bottom up. We first offload vector matrices and these low-level PETSc structures to GPU. And then we designed GPU subclasses for some PETSc types, especially vector matrices. And also we use twin arrays. We maintain 2 copies of the data on host and on device, so that difficult operations can still happen on host. So we can do incremental GPU analysis. So that's tail twin array. You can see we have a special pointer that pointer to a structure for device, and we allocate. We have the host array pointer and then a device array pointer, and we have a mask to maintain the synchronization. But it's not easy to maintain this mask. We need to carefully know when to update the matrix, and how the bugs could come from this mismatch. PETSc survived with the C plus MPI plus CUDA approach, and we didn't need to write a single source code for CUDA plus OpenMP, because there were no other GPU vendors until the ECP project. The problem for us was how to deal with MD GPUs and Intel GPUs. So we later come to Kokkos. This slide shows the three backends, GPU backends currently in PETSc. The first PETSc CUDA backend, that was the original backend, and we later improved on. The right one is the new Kokkos backend. I emphasize the Kokkos-Kernels because in PETSc we do not have many. We didn't read many kernels ourselves. We generally use vendor libraries. Kokkos-Kernels provide a nice wrapper for vendor mass libraries. So that's why we choose Kokkos. But at the beginning, the PETSc Kokkos backend performance was not that good, and AMD came up and they added a heap backend. So currently we have these three backend, and we tried hard to combine CUDA and heap because they were very similar. But it's not an easy process. Currently it's half done. So currently with PETSc, you can use this command line, configure command line to configure to automatically download Kokkos-Kernels and then build them. In PETSc, we treat Kokkos as a language, and we set up a Kokkos compiler and the specific suffix for Kokkos code. With the new C++ then, there were some difficulties to build Kokkos along with PETSc. For example, at some stage, Kokkos used a static inline variable of C++, and it caused problems in PETSc build script. So we have to figure out this visibility hidden flag, and we use a lot of features in PETSc in Kokkos. For example, Kokkos atomic, Kokkos complex, Kokkos parallel for reduce, and Kokkos plus from Kokkos-Kernel and sparse, also sparse. Kokkos batched, teamed IO, team inverse IO. So PETSc and Kokkos have deep integration. And a very last feature I feel is Kokkos dual view. Currently, we use dual view to manage the host copy and the device copy. And the last thing with dual view is if it's on unified memory, then these two copies are actually the same. So that's very nice. And we provide new APIs for PETSc Kokkos users. For example, you can directly get a Kokkos view from PETSc vector, and also we use Kokkos offset view. With that we can users can use PETSc distribute multi-dimensional view with global indexes. That's a very convenient for domain scientists. They want to have a simple view, global and then global index. Of course, we had some difficulty in adding Kokkos to PETSc. The first is GPU streams. GPU computation is asynchronous. If you want to have more parallelism, you want to have multiple streams. But how to use these multiple streams in PETSc? C code, we do not have a good approach because unlike C++ code, PETSc could not afford adding an extra stream in existing APIs. So currently, we only use one stream created by PETSc and stored it in a global variable and exposed to users via a inline function. A second difficulty is we don't know how to deal with scalar variables. So on the right side, I show a CG algorithm. You can see in these servers, we usually need to compute the norm or dot product on vectors, and currently these scalar variables are stored on host as stack variable. But if we want to offload the whole server to GPU, then how to deal with this scalar variable? Because we want to check whether the norm is good. We currently do that on host. What structures we should use to move these scalar variables to device? Currently, I have no approach. If I wanted to insert some C++ structure, then I could not reuse the existing PETSc server code. That's a headache for me. At the last, I want to show example. I do solve is with PETSc backend. First with PETSc GPU backend. On command line, I just need to specify the meta type. Currently, it's meta type AIG. That means type on CPU. You can see the red font, the execution time, and in the middle, I use the PETSc CUDA backend, another execution number, and on the right, the PETSc Kokkos backend. You can see PETSc Kokkos backend. The performance is worse than PETSc CUDA. Why? Because it's not a apple to apple comparison. Because Kokkos-Kernels, I find in some cases, Kokkos-Kernels could not keep up with the flexibility and performance provided by a Windows library. For example, with the Kokkos, I can store factorized matrix, the L part, U part, in the same matrix. But with Kokkos-Kernels, I could not do that. Also, in current Kokkos-Kernels, there is no incomplete choice-free factorization. So that's put us in a dilemma as to which GPU backend for us to recommend to users. I want to recommend PETSc Kokkos, but sometimes the performance is bad. So conclusion is PETSc already has deep integration with Kokkos. Currently in PETSc CI, we have 12 jobs testing with Kokkos. And from PETSc user mailing list, I saw more and more users starting using PETSc with download Kokkos-Kernels. So I'm very glad to see that. And we are planning to enable more PETSc classes with Kokkos. For example, dense matrix or block, CSR matrix, and even solvers if I have a solution for the scalar variable problem. Kokkos-Core and Kokkos-Kernels are key to make PETSc device portable. And we all benefit from closer collaboration. And we have bi-weekly meeting with Luke from Kokkos-Kernels. So I think PETSc Kokkos backend will catch up, maybe eventually replace other PETSc GPU backends, and so we can have easier code to maintain. Thank you.
Thank you. Questions?
Thank you. And why you choose the Kokkos-Kernels over SQL 1MKL for Intel GPUs?
Kokkos-Kernel, why MKL? Can you say again?
The question is, why did you choose Kokkos and Kokkos-Kernels as opposed to SQL and 1MKL?
Exactly. Thank you.
Because that's easier for us. In the PETSc Kokkos backend, we only need to call Kokkos-Kernels. And Kokkos-Kernels has the TPL support. If we want to enable the MKL, we just need to enable the TPL in Kokkos-Kernels, right? And if it does not exist, in my view, we need to add that support in Kokkos-Kernels instead of in PETSc. And I had PRs to Kokkos-Kernels to do this stuff.
Oh, hi. A great talk. Thank you.
Thank you.
Yeah, so PETSc historically has served a very broad user base.
Mm-hmm.
So you had users from Office of Science, you had students, you had postdocs, people from universities. How do you explain all of these new different build options to this very broad user base? How do you document and explain to them?
Build options. PETSc is well documented. So we have a quick installation guide, and we have called Slack channel. We use Discord, and we have PETSc user meetings and public mailing list. So we have very good communication with our users. So if they have questions, usually in minutes we will respond to them. We do that.